Okay, in this video we're going to talk about still finding volumes of areas that have been rotated about specific lines, but we're going to do that using a different method. So with the disk method and again the washer method, we were always thinking let's have these circles, these areas of these circles, and let's add all those up. So we were always thinking pi r squared. Well, the other method is called the shell method, and in this case, first of all, to draw the figure, I'm going to do the same thing. So I'm going to rotate this about the y-axis, the region between x and x squared, and so I'm going to duplicate this about the y-axis. So I would have the line y equals x, and then I would have y equals x squared underneath that. Okay, and so we get this region, this volume of this shape like this, and I'm going to go ahead and make it look three-dimensional by doing this. Okay, so I want to find this this volume. Now, using the washers, and this is what I talked about in the washer video, it's the same exact problem between x and x squared. What I need to do is if I rotate it about the y-axis or a vertical line of any sort, using washers, I need to make sure my functions are determined, are written in terms of y and not x. And sometimes that can be a little bit difficult. In this case, it's not difficult at all, and I showed you that on the last video, but it can be difficult to do so. So if you don't like doing that, if that's one thing that you really don't like doing, you can use the shell method. And here's how the shell method works. I want to think about these rectangles that I make whenever I find the area, right? So I take each one of these rectangles and think about rotating the rectangle around whatever axis it is that you rotate it about. So that would give me this same rectangle on this side, right? Same exact rectangle over here. And then what would I do with that? Well, that rectangle would turn into, let me change that. That rectangle would turn into kind of like a shell. I don't like that either. A shell that has this thickness of these sides of this rectangle, right? So whatever the thickness of this side of this rectangle is, as the thickness of the shell, but then in this case would be hollow on the inside, right? And so I take these shells where they're hollow and I keep stacking them inside of one another. So let me just do another one so you can see that they would just be stacked inside of one another over this region. So this one would be right here, right? And then let's think about taking that and rotating that around, and again that would give me this shell, which would then be on the inside of the shell that I had with the blue rectangle. So each one of those rectangles that I make for my area is going to give me a shell when I rotate it about. Okay, so the good thing about this is I don't have to change my functions in terms of y if I use the shell method instead of the washer method in this case. So here's what you want to think about. I would suggest you always draw at least one shell so you can see what you're looking at. But in order to find the shell, instead of taking the areas of circles and adding them up, I'm going to be taking the surface area of these shells and adding them up. So what would be the surface area of the shell? Well, the surface area of the shell would be 2 pi times the radius, right? That would be the circumference of the base of the shell, and then I just need to multiply by the height, right? So times the height, and then times the thickness, which we're going to think of that as being either dx or dy, whatever it happens to be. In this case, it's a change in x will be the thickness of the shell. and we're going to add all those up from A to B. And so that would give me my shell method. So instead of thinking about areas of circles, I'm thinking about surface areas of cylinders. So that's why a lot of people think the shell method is a little more difficult, is because I'm not just dealing with, area of a circle. I'm dealing with surface area of a cylinder, which is something that we're not necessarily used to. So this is what I always want to think, and then all I'm going to need to figure out every time is what are my bounds, what's the radius of each one of those shells, and what's the height of each one of those shells. Okay? And if I can figure those things out, I can set up my integral and I can evaluate. So the first thing you want to do is you always want to think about your shells, your bounds here are always going to be the area before you revolved it. So where did I have my rectangles? My rectangles were from 0 to 1, right? I have all these rectangles stacked in here from 0 to 1. I want to make sure that I don't try saying from -1 to 1, because this rectangle is this rectangle revolved. Okay, I didn't have a separate rectangle over here. Okay, 2 pi times the radius. So I'm going to go ahead and bring the 2 pi out front. The radius of the shell. So if I just think about the radius of each one of these shells, what is that going to be? Well, it's going to go from the y-axis out to whatever x value I'm determining my rectangle at, right? So it's always going to be determined by whatever the x value is for that rectangle. So my radius in this case is just x. My height of each one of these rectangles in this case is going to be the top function minus the bottom function. Now, you're not always going to have two functions there, but in this case I do. My height is always determined by x minus x squared. Okay, so that's my height, x minus x squared. And then my thickness is dx. The thickness of these shells is a change in x, a dx. And so what you'll notice is my integrals in terms of x here, as opposed to if I used washers for this same exact problem, I would have to change it to being in terms of y. Okay, so it's a little bit different there, but I'm going to get the same value whenever I integrate. The first thing I want to do here is make sure I distribute that x, and that's going to be x squared minus x cubed dx, and now I'm ready to integrate and evaluate. So 2 pi, the integral of x squared minus x cubed will be 1/3 x cubed minus 1/4 x to the 4th. And I'm going to, should be consistent here, I'm going to evaluate this from 0 to 1. When I plug in 0, I'm going to get 0, so all I need to do is essentially plug in 1. And I'm going to get 1/3 minus 1/4. If you want to put the minus 0, because when I plug in 0, I get 0 for all that, that's fine. 2 pi times 1/3 minus 1/4, getting a common denominator would be a 12th, so 4/12 minus 3/12, which would be 1/12. And I multiply that by 2 pi, and I get pi over 6. Okay, so that's using the shell method. Sometimes, if you can really visualize the shell, it makes it a lot easier than trying to do the washer. But they're kind of interchangeable. There are a lot of times where I could use either method. There are some times when I really need to use one or the other. But in a lot of cases, when I'm trying to find these volumes, using the shell and using the washer method can be interchangeable.